thoughts? What did we calculate here? What is this equal to? Energy of what? Does that clarify what we need to do? Huh? How many photons do we have? How many photons do we have? Debbie?
Should be 1 mole.
How many photons are in a mole?
No.
Avogadro's number. A number you should be familiar with. Just like you're probably okay. So we got our answer. Plug and chug gives us the energy of 1 photon. Multiply times Avogadro's number, that gives us the energy of 1 mole of photons. Make sense? Does this have more or less energy than a mole of yellow photons? More or less energy than a mole of yellow photons? So you have your whole electromagnetic spectrum, right, ranging from radio waves to gamma waves. And then we have our visible light spectrum. So this is increasing energy. That's why this kills you, and this doesn't. We cook our food with this.
We do not prefer that.
No, otherwise we'd all be dead. Make sense? Meaning we are starting with some energy stuff and then going into quantum mechanics. Okay. Good with this stuff? Sweet. Next, we'll talk about electron levels. I guess raising purple today. In fact, in the 3 years of my tutoring and SIing, I've never made a marker into the trash can. Anywhere. Not here, not the library. All right. So we have these various levels of energy for electrons. All right, they can hypothetically go up to infinity with whole number integers. What's important to note here is that the distance from, we can call this 1, I, ground, the distance between 1 and 2 is bigger than the distance between 2 and 3, which is bigger than between 3 and 4, 4 and 5, so on and so forth. So the distance and accordingly the energy change from the levels decreases as you go up. So if you have an electron here, it takes more energy to excite it from 1 to 2 than it would to excite it from 3 to 4. Does that make sense? The change in energy from that movement is characterized by the Balmer equation, which says that 1 over our wavelength is equal to constant R times 1 over our final level squared minus 1 over our initial level squared. And this R is equal to 1.0974 times 10 to the 7th. Please don't memorize that. So, we'll start out. Well, I want to see what you guys can do from this. We'll start out with a more challenging problem than usual for the first example. What is the change in energy for an electron? And the last stuff we were working on, we were working with photons, and also just as likely be applicable to electrons. What is the change in energy for an electron that is excited from the second to third levels of shells? What is the change in energy for an electron that is excited from the second to third level of shells? Try to work this out. Don't be discouraged if you get stuck. But I know you are able to do it. These are your ends. Thoughts? Anybody know where we should start?
Put your ends in the denominators of the fractions in the parentheses. The first one would be the third, because it's the final. The second one would be 2, because it's the initial.
Like this?
I think.
Yeah. So we're just plugging values in right now. Sorry, this is a minus. Okay. So this would become 1/9. This would become 1/4. Anybody have that? Those with calculators. What do we get? Katie, did you calculate it? Were you able to calculate it?
Hold on. I think so.
This here?
I think so.
What did you get?
Negative 1524166.667.
Okay. Now what do we need to do? So we have 1 over our lambda equals that. So our lambda is equal to 1 over 1524167. What did you get? I think you're the one that's doing it back right.
6.561 e to the negative 7. There's more, but I don't feel like
Okay. Probably negative, right?
Yeah.
So negative 6.561 times 10 to the negative 7. This is in meters. How do we go from our wavelength here to energy? Right. Energy equals hc over lambda. Remember, in this case, our lambda is in nanometers, so we should convert this to our nanometers. How do we do that?
Oh, 5.
What's that? How do we convert meters to nanometers? How many nanometers are in a meter? How many go up? What? No, not a million. Sure?
Trillion.
No, not a trillion.
Billion.
Billion. Remember your unit conversions. 10 to the 0 is your base. 10 to the third, negative third is milli. 10 to the negative 6 is micro. 10 to the negative 9 is nano.
Getting screwed up on the right hand side.
So 10 to the negative 9th meters in a nanometer. We get a negative 656.1, let's say 656 nanometers. Why is this number negative? How can you have a negative wavelength?
Electrons.
Good thought, but no. What causes this number to be negative? If we think back to our original equation, what causes this number to be negative? No. You can subtract your things, it's still a positive number. What matters is that this number is smaller than this number. So when does that happen? Well, that happens when our final So this is what happened, right? So when our final is a greater energy level than our initial, let's do the other equation and then that'll make sense too. Why does this work so much? Okay. So we end up with negative 656 nanometers. What do we do with that number now? Our energy equals hc over lambda. Our h is Planck's constant, which is 6.626 times 10 to the negative 34. C is 3 times 10 to the 8th. Maybe you might have been given 2.998 or something. Here we use 3 divided by our negative 656. This is why that negative is important. Because we don't care what the numerical value of this is, we're going to get a negative change in energy. And this question would be a little more clear if I asked how much energy is released. So if we're requiring energy, a negative energy is being released. Does that make sense? Let's do double negative. Does that make sense? No, it does not make sense. What is confusing? So what we're calculating here is how much energy is released from changing from our second energy level to our third energy level. If we did it the other way around, we would have 1/4 minus 1/9. And if we did that, we would have the exact same thing, except we would end up with a positive number here.
Right. So why did you change it to how much energy is released? Because no energy is released, right?
Right.
Energy is taken away from surrounding.
Right. I changed it because it makes it a little bit more clear so that it doesn't get confused with the work conversations we were having a couple weeks ago. Because if your delta energy, if your change in energy is negative, based on those conversations, you would say that energy was released from the system, right? So I didn't want that to conflict. That's why I changed it there. So you're right, no energy is released, energy is required. So if you were to say a negative energy is released, that would mean energy is absorbed. Does that make sense? Any questions on this before we move into quantum theory?
So you'll go no further with the energy equation?
Did she go any further? No. No, this is all you need to know energy-wise. You might see one other equation that we basically addressed, and that's that delta E is equal to RHC times 1 over n final squared minus 1 over n initial squared. But all this is combining the two equations that we used. Right? If you know that energy is equal to hc over lambda, and you know that 1 over lambda is equal to r 1 over n final minus 1 over n initial, then if you multiply through and isolate your energy, you'll end up with this. Does that make sense? Fantastic. Okay, into quantum mechanics. Is this stuff making sense at all right now? Not this stuff, the quantum theory stuff. What does no response mean? Is this stuff making sense right now?
I'm not exactly sure what these is in quantum mechanics, I can't remember.
For you guys, your quantum numbers, so NL, M sub L, and M sub S, and your electron configurations. Have you guys gotten to electron configurations yet? Probably not just yet. So, like in the next couple of days. All right, we'll dive right in. Stop me if something seems confusing. So, quantum mechanics basically uses quantum numbers to describe electrons around an atom. So, whenever we're talking about quantum numbers, we are describing an electron. If you want to think of it as an address for an electron, that is a pretty good analogy. So, we have our various quantum numbers. Quantum numbers. First of which is n. So we've already seen n. This is the same n. So our n is our principal quantum number. And it describes the shell that an electron is in. And tells us the size of the orbital. I'll talk about orbitals in a minute. So describes the shell and tells us the size of the orbital. And n can range from, so n can be any positive whole integer. Right, so n is equal to 1, or 2, 3, so on and so forth. N tells us basically the size of that shell, how far the electron is away from the nucleus. Next, we have our L. And L is our angular momentum quantum number. Angular momentum quantum number. This describes the subshell. And the subshell is a collection of orbitals with the same shape. So a collection of orbitals with the same shape. And accordingly, it tells us the shape of the orbital. So N tells us the size of the orbital, whereas L tells us the shape of that orbital. L ranges from 0 to n minus 1. So this notation shows an interval, so 0 to n minus 1. So for example, if you have an n of 2, your possible L's are 0 and 1. If you have an n of 3, you can have 0, 1, and 2. For our L's, L of 0 is spherical. And is noted as an S subshell. For an L of 1, we have a dumbbell. Oh, I didn't bring balloons. Never mind. Dumbbell shape. Not bring them Thursday. And we call that a P subshell. For an L of 2, we have a, let's say, a 3D clover looking thing. So you can think of it as 2 P subshells, and that is the D subshell. And for an L of 3, we have, I don't know what word to use, but basically your D subshell plus another one if you imagine it coming out at us. Right, so you have your X, your Y, and a Z going through. Does that make sense? Kind of like a jack. If you know what jacks are. And that is our F subshell. So S, P, D, and F. Real quick. So a term here to know is a nodal plane. Nodal plane. Nodal planes are areas where the probability of finding an electron is 0. Probability of finding an electron is 0. For an S subshell, there are no nodal planes. There's no plane that we can draw through here where we will not hit a region that could contain an electron. For our P subshell, however, we have one nodal plane. And if you imagine 2 balloons up and down, and there's no chance of finding an electron where those intersect, Our D subshell, we have 2 nodal planes. And our F subshell, we have 3 nodal planes. I can't exactly draw them. Okay, so it's an area where the probability of finding an electron is 0. Next, we have our M sub L. So M is a subscript L. This is our magnetic quantum number. And it tells us we'll say describes the subshell. This describes the orbital. It tells us the orientation of the orbital in space. Okay, so if you imagine your P subshell, which basically looks like this, right? It can either be this way, or this way, right? Your X, Y, and your Z. So our P subshells have 3 possible orientations in space. And we'll come back to that in a minute. Our M sub L's range from, it also tells us the number of total orbitals. And our M sub L ranges from a negative L to L. So for example, if we have an L of 2, our M sub L can be negative 2, negative 1, 0, 1, and 2. So those are our possible M sub L's, from negative L to a positive L. And our fourth and final quantum number is M sub S, and that is our electron spin quantum number. Electron spin quantum number. It describes the electron. It tells us the spin of the electron. And our M sub S is either negative 1/2 or positive 1/2. So our only 2 possible values for our M sub S are negative 1/2 or positive 1/2. All right, is this making sense so far? So basically what we're doing is identifying everything we know about the location and spin of an electron. Does that make sense? Now I'm going to attempt to draw this.
So a subshell is kind of more like based on the location in the periodic table, like by row.
No, that's your shell. So your shells follow the the periods of the periodic table. Subshells are more of a category of orbitals. So each shell has an s orbital. Subshell basically indicates that it is spherical, right? Regardless of what shell it's in, it's a spherical orbital. Does that make sense?
So like the S, P, D, F, G are all subshells.
Right.
And then those like whatever shell that subshell's in, is like how far away from the nucleus.
Right.
Okay, and then an orbital is just like where it could be, where the electron could be, it's like describing where it could be.
Yes. So orbitals contain up to 2 electrons, and basically is a probability map of where an electron might be. So let's try to visualize this. I think this will help, but it will turn into a mess. So, that was almost pretty good. If this is our nucleus, we have our first shell. And so this is an N of 1. For an N of 1, what is our possible L's?
It'll be 0.
0. All right, because remember L ranges from 0 to N minus 1, and 1 minus 1 is 0, so our only possible L is 0. That means we're only going to have a spherical orbital at our N equals 1. Every orbital contains 2 electrons, so this can have 2 electrons. Following so far? This is why, if you look at your periodic table, period 1, those 2 atoms, hydrogen and helium, are stable with only 2 electrons. That's why hydrogen only makes 1 bond. Or when it becomes an ion, it gives up 1 electron and it's stable there. Does that make sense? So carbon has to make 4 bonds because it wants 8 electrons. Whereas hydrogen only has to make 1 bond because it only needs 2 to be stable because there's only room for 2 in the first shell. Does that make sense? Next, we have our second shell. N equals 2. So for an N of 2, what are our possible L's?
0 and 1.
0 and 1. So that tells us we can have an S subshell and a P subshell. So first, we'll talk about our L of 0, basically our neutron. All right, so this is our N2L0. What are our M sub L's for an L of 0? Zero. Because M sub L ranges from negative L to positive L, negative 0 to 0, it's just 0. And that makes sense because a sphere can only be oriented one way. Doesn't matter how you turn it, it's still just going to be a sphere. Make sense? Cool beans. Now we'll move on to our L of 1 within our second subshell. So that is our dumbbell shape. So that would tell us, still we're in the second shell, but now our L is equal to 1. So with an L of 1, what are our possible M sub L's? Taylor.
Oh, for which N?
For an L of 1, what are our possible M sub L's?
-1.
Negative 1, 0, and 1. Remember, M sub L tells us the number of total orbitals. So we have 3 possible orientations. That means we have 3 possible orbitals within this subshell. Does that make sense? Is subshell making a little more sense now? Okay. So we can have that one. We can also have this one. Right? Doesn't matter which one we call what, method me. So this can be our -1. This can be our 0. And then you have to imagine that 1 is coming straight out at us. And that would be our M sub L of positive 1. Does that make sense? And we could keep this going, but this will become a tangled mess pretty quickly here. Okay. So, the energy diagram that we started with gets a little more complicated because you can have electrons. Hypothetically, if you put enough energy into it, your electron could go from an n of 1 to an n of 2. But it's more likely maybe to go from an n of 2 with an L of 0, so from that spherical subshell into one of the p subshells, because that's a smaller energy change than jumping an entire shell. Does that make sense? Cool. So, where are we at? 5 minutes. Let's save electron configuration for Thursday, because you guys haven't done it yet. But first, we'll do a couple examples. I'll just do one multiple choice example, and we'll call it a night. See, now it goes up just fine. What the hell? All right, so if a particular electron is in the second shell, what is a possible set of quantum numbers to describe it? Okay. Of A, B, C, D. Ooh, I told you we have an n of 2. All right. So you have an electron in the second shell. What is a possible set of quantum numbers to describe it? So A, we have 2, -1, 1, and 1/2. B, we have 2, 0, 1, and -1/2. C, we have 2, 1, -1, and +1/2. And D, we have 2, 0, 0, 1. What's the answer? Well, you already know all the answer, right? Not just those. Can we have an L of -1 if our n is 2? No, right? Because L ranges from 0 to n minus 1. So we can't have a -1. So that's out, which means our A is out. Can we have an L of 0? Yes. Can we have an L of 1? Can we have an L of 0? Yes. Okay. If we have an n of 2 and an L of 0, can we have an m sub L of 1? No. Remember your m sub L follows your L. So your m sub L goes from a negative L to a positive L. So yes, if our L was different, at the second shell we could have a 1 for m sub L, but we would need a 1 here also for our L. So that doesn't work. So B's out. C, can we have an L of 1? Can we have an m sub L of -1? Can we have an m sub S of 1/2? And that one works. Let's look at D. Can we have an L of 0? Yes. Can we have an L of 0? Can we have an m sub L of 0? Yes. Can we have an m sub S of 1? No. Remember, m sub S are only -1, -1/2, or +1/2. So D is out, and you have C. I promise you, you will see questions on your final that are just this. Any last minute questions? Cool beans. You guys have a good one. How's your stick biology? I'm going to get the drink of water. Hey.
Look at those rules. The front? Okay. Oh, so everyone was in it.
We didn't do this already?
Yeah, let me just read
Whoa,
this.
fuck.
This is this is what we learned pretty much today. Or yesterday and today.
It's quantum mechanics.
Actually the past 2 days I've been watching some YouTube videos on it that go into even more detail about how it was like originally I guess thought of. And it's pretty cool. Like hydrogen looks cool. Or hydrogen electron, but cool.
Yeah, I definitely don't understand that, so we're gonna need to do some extra work. I feel like a bad person. I'm not attracted to him at all, but he has a nice truck and he can build things.
So he's a handyman with a truck.
Yeah, but he's not cute.
Most guys with trucks aren't.
You're really cool out.
Called out the majority of the guys here.
Yeah,
It's okay. I want a truck when I'm older, but not like 6.7 liter power stroke. You know, I don't want.
Aiden, I have a type and it is not good because anyone who's my type is probably a bad person and will treat me like shit. So then I told myself, hey, if the not cute ones are going to treat me like shit, might as well only date the ones that I find attractive.
See, I just want a girlfriend that like FaceTimes me all the time.
Really?
How are you and Martina doing?
Good, but
Does she FaceTime you?
no,
Oh.
Did you tell her that you wanted that?
no. But it's also not a part of like, hey, I want this out of a person, so you should give it to me because I want it. It should just be like, I provide this to the relationship, which I like, you know.
Do you FaceTime her all the time?
No, I don't even think we haven't exchanged phone numbers yet.
So are things actually going well, or?
Things are great, yeah, we're gonna hang out tonight. Most likely.
Ooh.
Yeah.
Yeah. You guys need it.
Come in.
I have another piece of scrap paper. You know, given the fact that you have an exam tomorrow, I would have expected a better turnout.